I'm Brandon Bercovich from Uber. I'm an engineer there that works in the compute platform. So my talk is designed for failure, how to manage thousands of hosts through automation. Wasn't really quite sure what I should put in the title based off of legals requirements, thousands, tens of thousands, X, so just sticking with thousands. All right, so today we're going to be digging into three problem spaces. We're going to talk about resource utilization, fleet management, individual host management, where we started in each of these, kind of like a history of how we evolved from, I'm sure some of you know the explosive growth Uber's had when we started with a very small number of things and quickly moved up. And how those things progressed as we started design for failure as a first class ask. We're going to be limiting the scope of this talk to stateless services. There is an overlap between a lot of the stuff we do with stateless services and stateful services or batch workload, but there's only so much time we have, and a lot of those caveats are really business specific, whether your jobs are idempotent or whatever requirements you have, and they can very be individual based. So, at some point, given enough hosts and services, there's going to have that conversation about how can we use the resources we have more effectively. So we want to save the company some money. We may start trying to co-locate services. Maybe we'll have some services that need a lot of disk, but a bunch of services that don't need disk, or high memory services with high CPU services, and any ways to utilize the resources we have more effectively. So our first try of this was pretty naive. We manually placed services on host with no resource isolation. We didn't plan for failing hosts, so when a host failed, we had to manually reschedule that service somewhere else. If somebody said, oh, we only need 2 cores, but ended up using 4 cores, well, we didn't have a way to stop them, so they could cause noisy neighbor issues. Or if they just said, okay, now we need to start using more resources, we had to manually rebalance the whole cluster to bin pack that more effectively. So we really needed to solve these problems as we were growing. So, why should we fix 2 problems when we can fix 1? So we decided to adopt containerization to have a better user experience for the apps that we're running first. In our case, we used Docker to ensure services weren't going to use more resources than they requested. However, we still had the same problem where we were using manual placement. So again, if a host failed, we needed to move the services to another host. When services needed more resources, we'd again have to manually rebalance that. So, this was a good first step into containerization, but we really needed to move to something a little bit more automated. So in this current attempt, we solved this problem using Apache Mesos, running the scheduling framework Apache Aurora, both open source, to schedule the workloads within these containers. This allowed the services to get rescheduled when a host goes down or rebalance when resource requirements changed. So now the system was taking care of putting things where they needed to go in the boxes that were available. In just a really oversimplified example of how this works, a scheduler will place a service on a host. If the host stops running or fails, the service is no longer running, right? The scheduler itself will detect that service isn't running and launch it somewhere else. And similar workflow happens when more resources are needed. The scheduler will place the logic container on a host that has more available resources. So now the fun part. I don't get paged when a host goes down. The service gets rescheduled. The platform itself is designed for resiliency when we have failures. Just want to say a quick note about schedulers. There's a lot of various options out there for scheduling, so there's not a real reason to manually place services yourself. I would say Kubernetes is probably the most popular one right now. Mesos is the one that has the largest proven scale that's still open source. There's also OpenStack and Docker Swarm and various other ones that I don't have a lot of experience with, but really they can solve your individual needs, and you should look in to see which one is best for you and make it fit. In our case, and other companies' cases, Mesos was the best fit for us, but Kubernetes is getting a lot of traction. So now that we have service scheduling that's designed for failure, we want to move on to the fleet management, right? So how do we upgrade our scheduling software, or how do we do maintenance across the fleet, like a kernel upgrade, or as you may have heard in the keynote, Meltdown or Spectre or any of these other really high impactful security responses that need a quick update across your fleet. Well, we started using this solution we had, right? We started with Puppet, which in general I'm a big fan of. However, in our case, Puppet wasn't doing what we wanted it to do. And this was partly the way we had it set up, and part to just what we were doing with it. We could update a version, and then Puppet would roll out across the fleet, but we could potentially change our service scheduling software and configuration at the same time, not to mention anything else that was getting pushed out unrelated. In this example, our hosts are getting an agent upgrade and an unrelated pseudo file change across the fleet at the same time. Now, you may see an issue and you're like, is this related to some new package that got installed from our base hosts, or was this a aspect of the scheduling software, or did we also change the configuration, or whatever the case? So we wanted a little bit more control. So we built a little orchestration layer called Platform Lifecycle Manager, or PLM. Now, a lot of these problems that we were trying to solve with this software are actually solvable with Puppet. But they're a lot easier to solve if using a Puppet master. But due to our size, we were running a masterless Puppet environment, and there was a lot of extra hoops there. So we decided, writing this little orchestration would be a little easier to roll across the fleet. So as you can see in this example, it took down the hosts and put them into groups, right? Maybe we start with 5% of the host and 10% and so on until we can roll out it across the fleet, right? Oh, great. We have a controlled rollout in the manner we want. Well, let's roll out that change. This change is kind of breaking. It requires we drain this workload. Let's do it. Maybe let's just pick a batch size of 50, right? That's a small percentage of our fleet. Wait, what do you mean we caused an outage for a service? Oh, we just happen to take down all the hosts running this specific service? Well, we should probably make sure that can't happen again, right? So there was a couple issues with our first version of this. We weren't paying attention to what was running on the boxes because we're like, everything gets rescheduled, it's no problem. But if you take everything down and it gets rescheduled at the same time, that can be impactful to a user. Additionally, there was a few more issues. One, and I can't stress this enough, the team that was performing the work wasn't the ones that was creating the tool, and they weren't closely involved with the team creating the tool. So there was some misunderstandings of what people actually needed this tool to do. Additionally, we were transitioning tech stacks, and this tool used our old tech stack, and we really kind of wanted to modernize it. So, we wanted to solve these problems. So obviously the first most important thing to solving a problem like this is to rebrand. That problem was a PLM problem. You don't need to worry about that. Now we use Cluster Lifecycle Manager, or CLM. So the new CLM tool was designed and engineered in collaboration between the two teams that were actually going to be using this tool. It made sure that we understood what we were trying to solve, and in a way that it needed to be solved. On a side note, just stress again, the people using the tool should have to be involved with this process. You have to give the input and make sure they're doing it. So in this case, we just put a check in place to say, okay, before we run this job, let's check with the scheduler and see if we're going to violate an SLA. Like, for example, maybe we want to make sure the service has 90% of its instances up for more than 10 minutes. Or we're not going to take down more than, or not reduce the capacity of the cluster by more than 10%, right? So that we are ensuring we're not affecting the overall health of the cluster. So in this case, just in this example, there's the same batch sizes, but there's a group of hosts, and there's only a couple services, and all the services are individually unique between those groups, so that we weren't impacting anything too difficult. So the way this works is we would launch a job, say maybe you target 50 hosts. We get back a message that says, okay, of the 50 hosts you target, these 46 are safe to drain. These other 4 are not. They would violate an SLA. Or, for example, we wanted to do, like a kernel upgrade or whatever, where you want to do a large number of hosts. It may say, okay, you're trying to drain 100 hosts. You don't actually have the capacity in your cluster to do that. You can only drain 84 hosts right now. So we made a generic way to enforce business rules on our jobs, and the first thing we do is check against those business rules to see if this job was able to operate. And it was very easy to change those as our requirements changed without having to rewrite a lot of code. Great, so now we don't have to worry about hosts going down since the schedule will reschedule it. We don't have to worry about disturbing services because our fleet management takes care of that. But what's going to happen to those hosts we didn't drain since we violate the SLA? Oh, let's just try again in 10 minutes. Great, well now 3 of those hosts can be drained. What about that last one? Well, we could wait another 10 minutes. Well, what about the host that went down? One host is fine, but what if we lose 10% of our hosts over the month? Do we have enough capacity for that? Sounds like a lot of work to do manually. We should automate this. So now that we're designed for failure, the question is not how to upgrade a host, it's how a failed host gets the right information when it comes back up. So we solve this by changing CLM to use goal state to handle convergence. So we store our goal state in a Git repo, we store some actual state in a cache, and we use CLM to detect the differences between the goal state and the actual state. We dispatch this work to Cadence, which is our orchestration engine that's open source from Uber. And these workers get that information and send the remediations off to hosts. So instead of sending out a request to a list of hosts, we simply just change the goal state of a cluster. When a host is up and reporting, the information we compare, when it's reporting in information, we compare that information to what should be there and write an issue if the information doesn't match. The remediation scheduler or the dispatcher schedule remediation for those issues to correct it, and we use some rate limiting to help with the orchestration. So now we don't worry about upgrading when a host is down because they'll eventually come back up and get on the right state. In general, this architecture was designed with resiliency as our first thought. All these components are local to an availability zone. So if one zone's down, you can still operate in zones that are up. The workers, detector, dispatcher are all stateless. The cache is used for convenience and can be bypassed or rebuilt quickly. The stateful parts of the system are Git repo and Cadence orchestration engine. And the Git repo can be bypassed with local configurations files to make bootstrapping a new environment easier. But we aren't only concerned about upgrades, only partially going out now. But what about host failures, like a host is down? So with the system, our detector doesn't always have to look at the goal state. It can also look for known things, like a host is up or a host doesn't have any errors in our monitoring system. So in our case, the detector knows the host should be up and reachable by SSH. If the host is unreachable, it will try a simple remediation like a reboot. If the first remediation doesn't fix the issue, the workflow will escalate to another workflow, in this case maybe an RMA. Before this system was put in place, we would get hundreds of alerts each week for hosts that could be handled automatically. Just simple, either bad hard drive or kernel panic or something else that just required a real easy, simple fix. That when you've got a couple hundred hosts, it may not seem like a lot of work every week to reboot a host or two, but when you're dealing with thousands and thousands of hosts, it quickly became more work than any person should do when you don't have to. So I'm going to dive into a little bit of the individual components a little bit more. I mentioned Cadence is an open source engine that we use. It's distributed, highly available. It's developed at Uber for a way to execute asynchronous, long-running business logic in a scalable and resilient way. The business logic modeled as workflows or activities. Cadence's sole purpose is to orchestrate activity executions. The workflow and activity implementations are actually hosted on the executors in the worker process. And those workers long poll the Cadence server for tasks. They execute that task by invoking the workflow or activity implementation and return the results back to the Cadence server. Furthermore, the workers can Furthermore, the workers can be implemented as completely stateless services, which in turn allow for horizontal scaling. The cadence server itself brokers and persists the tasks and events generated during workflow, which they have certain about scalability and reliability guarantees for those workflows, but the individual activities themselves are not fault tolerant. They can fail for various reasons, but the workflow that defines in which order and how activities are executed is guaranteed to continue execution under various failure conditions. You could have a activity that fails, but your workflow says, hey, if this activity fails, try it a couple more times or do this other thing, and the workflow will ensure that action is taken. So the cadence server itself uses Cassandra to persist the information. So we store our goal state in basically some Git repos with a little logic built on top to help validation. So each cluster we have has its own goal state, and any changes to the goal state are validated against the cluster goal state schema before any commits to ensure we have them in the right format, that they didn't violate some business rule that we said. For example, maybe we say let's use a new version of Mesos for our agents, and that version doesn't actually exist. We don't want to push that out and try to validate that, so we've got a little validator that can check what we put in to be like, oh, yep, that is a proper version that's formatted correctly and it fits the rest of the schema. We also store a list of all our availability zones and clusters in each of these zones, which is validated against a similar clusterless schema before commits. We treat these files as the source of truth for what we have running in a cluster. How many hosts should be in a cluster, what version of the software, and where they should be running. So when there's a discrepancy, this is what's used, and if we want to add more capacity to the cluster, we up this file, and then capacity will come in. So our cache, which I've been talking about, it's actually an internal graph database. And we use this to co-locate information from various sources just for convenience, like monitoring systems, inventory management, and information from the host itself. In our fleet, we query the cache for problems instead of tens of thousands of hosts directly. When we detect an issue, though, we check the source of truth before proceeding with remediation. This greatly reduces the calls out for data in our system. Since multiple systems are using this cache, we're not repeating any work. So, instead of, like I said, scanning the tens of thousands of hosts, we'll find the handful of issues and then check those individually to make sure that they are still an issue before we go on. So the data from the host can be pushed up to the cache or pulled into the cache on a regular interval. The data can fully replace the set, or delta can be generated. In our case, for issues that we're finding, they're pulled into the cache as a full replacement. So when we fix an issue, we don't need to then go ahead and delete that issue from the cache. It'll just no longer be present after the next issue generation runs. That data is sent to the cache, which includes the age of the data, so that we know how stale it is. The requirement for the cache is very dependent on your environment, right? So depending on your needs, the information sources you have and your various other setups, you could go with a graph database, you could go with a different type of database, you could go with a generic cache or like Redis or Memcache or whatever, or you just skip it all together and just read directly if you have an environment that would be effective for that. So we tie that all together with CLM itself. Why do we build this? There's a couple existing solutions out there that perform similar functionality. This is really just a lot of internal business logic for Uber. It's talking about the rate limiting, talking about escalations, talking about what to do, mapping things together, right? There's other things that do that, right? But when we looked at those solutions, there was various reasons why for us it made a little more sense for us to write this. They were using different tech stacks. We didn't want to turn up some components that we would use only for this. For example, one of the solutions we looked at used RabbitMQ and MongoDB. Those are great products, but in our current environment, we don't use those, and we didn't want to bring up two new components just for this one tool. Now, you could be arguing, well, supporting those two new tools would be a lot less time than rewriting a whole new solution. And you know what, you're probably right. But there's a lot of work that needs to be done anyways when writing that business logic. So we didn't feel like we were saving that much time, and especially when we were planning for the long term, it was just two more components we didn't want to add to our dependency environment, to the management, and we just wanted to simplify things. So as I mentioned before, the CLM detector reads from various sources to find issues and writes those issues to the cache. The dispatcher itself determines which issue has a higher priority, since there's really no reason to fix like maybe a service problem on a host if the host needs to be re-provisioned or RMA'd. And we use some rate limiting to ensure we don't take down the whole fleet. So those are all sent off to Cadence, our orchestration engine. And let's say, for example, we want to upgrade the kernel across the cluster. We want to make sure we don't impact the capacity of that cluster, so the dispatcher is responsible for all that. Additionally, we're using a small MySQL database for simple locking and some history of what we've done. It's not in the critical path of this solution, of this product. It can still work without it. There's just some functionality that's not as clean without the enhanced locking we're using in a stateful environment. And we're looking into other ways to handle this function. Not that we don't like MySQL, we just want to reduce our dependencies. Our orchestration engine, Cadence, is already using Cassandra, so we may end up trying to use Cassandra, even though MySQL is probably a better solution for what we're doing with this. Just to, again, reduce what we're doing, because we're very focused on the resiliency and the lower dependencies, because this is a low layer of our stack. This manages our Mesos cluster, which runs a lot of our microservices and most of our compute environment. So this needs to come up very early in the process. And with that, I'm ready to take some questions if anyone has any. Thank you.
Okay, the microphone's up here.
So you guys said you were using Puppet before, but you wanted more fine-grained control of when and how some of those changes got deployed. Are you still using those, and how do you integrate this orchestration with whatever configuration policies you have?
Yeah, so to be clear, we still use Puppet, but we use Puppet for other aspects. What really, one of our first implementations of CLM still used Puppet to orchestrate what we wanted to do. So for example, just our initial setup was roll out a zone at a time with some canaries first, and then have some splaying done. But the issue is that Puppet didn't have any insight into placement of services. So we could potentially, even if we were rolling out to these canary hosts, they could all hit the same number of hosts that are running this one service. So the first version which we did was we changed it to where on these hosts, Puppet wouldn't automatically make any of these changes, and our orchestration engine would target which ones we wanted to run, and then run Puppet on those hosts individually. And then as we moved to more isolation, we really wanted to ensure that when we changed something, we were changing only one thing, so that if we had a problem, we knew what the problem was, and not the potentially other things that someone else rolled out, like a new version of SSH or whatever. Did that answer it? Okay, thanks. No pressure. Sure, please. Save me.
Can you go over the dispatcher again, how the CLM dispatcher actually works?
Yeah, sure. So the dispatcher basically is just an interpretation of business rules and rate limiting. So basically, it looks at that cache and sees, okay, are there any issues? All right, I've got 10 issues. Let's say I've got 3 issues on one host. Which issue is the highest priority? And do we already have something right on that host? Is there already a job that's running remediation? So it will determine which job to run, and it will send those workflows off to the orchestration engine. I talked a little bit about workflows having escalation paths. That's not really in the dispatcher itself, that's in the workflow. So, for example, like I said, a host is unresponsive, we reboot the host. If it still doesn't come back up, maybe it's best to RMA the host. That's an escalation in the workflow itself, which those cadence workers are really specific to the service. So we have like a CLM cadence worker. When you look at, also mentioned Cadence is open sourced at github.com/uber/cadence. The Cadence server, is generic, and you can have it connect any number of workers. But the workers you implement themselves have your workflow logic in there. So when we're dispatching those, we're just telling it to run this workflow, and then the workflow or the workers themselves have that logic on when to go to the next step or not. Did that answer? Yeah? Okay.
So how do you all manage the bootstrap and setup of CLM itself?
That's a great question. So because it's pretty low, we have a foundational stack that is very, very simple. And you know how I said there's no reason to do manual placement of a service? Mm-hmm. Well, we do manual placement of a service, but it's just like one service. So basically what we do is we have a very simple component that says, okay, these are for low-level infra services. This service should run on this host, and what it does is it downloads a Docker container and starts the Docker container up on those hosts. If that host is no longer, or if that service isn't running anymore, it will restart that. And if a host gets removed from the group that says it should be running, we have another service that will allocate a new host to that and schedule it back up. Now, we don't have the automation in place to automatically detect the bad host. We'd have to remove it, but we do have the automation in place to at least start it up and put hosts in. And because it's a very small number, we're working through that.
Thank you.
Yep.
One more question.
Who's the lucky person?
Thank you very much.
I'll talk to you later. Thank you.